Here we go. We're talking about statistics. This is like your preview of what you're going to do in AP statistics a little bit, or normal statistics. It's the precursor. So when you get there, you'd be like, I saw it here. We're talking about measures of dispersion. What I want you to do is, you're going to see on this sheet, the following is a sample of scores from a recent math test. And you see on one category it gives the scores, and in another category it gives the frequency. Okay, what's the name of the topic we are exploring right now? No, we finished probability. We're in what? Nope, that's the aim. We're in statistics. There is a button dedicated to this entire topic. You hit the stat button. Everybody do that. You should be on this screen. And then you hit enter on the edit screen. And what you want to do is, these are lists. This is where you enter data, like from experiments and stuff like that. Now, some of you have calculators from another class. And so what I want to show you is, suppose you have some stuff in this list that isn't yours. In order to clear out the list, go up to L1, hit clear, and then push the down button. It will clear the lists. You can move along lists by moving to the right or to the left. Make sure that you're on L1 and L2. Is everybody there? Good. What I want you to do is, I want you to enter the scores into L1 and their frequencies into L2. So 96, 84, 80, 76, 68. Then you push the right button, and we're going to enter their frequencies. And we've got to talk about what this means. Back. Now let's talk about what this means. This first category was the scores. The second category was the frequencies. That's an efficient way of writing the following out. What it really means is that there was 196. There were 5 84s. 84, 84, 84, 84, 84. You know how annoying that is to write out? There were 3 80s. 80, 80, 80. There were 6 76s. Are you getting the point? It's really annoying, and it's easy to make a mistake when stuff is written like that, so this is an efficient way to organize it. Okay, so you enter stuff into list 1 and list 2, then hit stat again. You're back to this screen. We need to make a calculation, and for this class, no matter what, you are always using one variable statistics. I understand there were 2 categories. You guys are only using one variable statistics. Hit enter. Now here's what you need to tell your calculator. Calculator, please pull the data from list 1, comma, list 2. Okay? So you put this in and then you hit enter. And you get every piece of data you could ever ask for. Okay? Here are all the pieces of data. Here are all the pieces of data. Now, please, take a minute and write them all down. Write them all down. Why did I, so X bar is the mean. These two, they stand for summation x and summation x squared. So this is all the data added together. This is all the data added together and squared. They are completely unimportant for this class. I'm going to talk about the rest in a minute. Just take it all down for a second. Here we go. All right. So here's the deal, right? You write down all these numbers, for anybody else watching, come from this right here. This is all the numbers that I'm going to show you on the board. Okay. So the x bar is the what? X bar is the mean. It's the average. Awesome. We don't have to calculate it out by adding everything up and dividing by the number of items anymore. We can just let our calculator do it. SX and this funny looking symbol, these are the standard deviations. This one, SX, is the sample standard deviation, and this funny looking one is the population standard deviation. Now, in the data, it says the following is a sample of scores from a recent math test. Do you have all the scores? No. You have a small sample. So which one are you going to use, SX or this one? SX. Do you get it? Okay. N. N is important because N is the number of pieces of data. If you make a mistake, okay, one thing you might want to check is, did I enter everything in correctly? And what you can do is you can count the frequencies that you entered in, Like watch. Let's go to stat, edit. Count these numbers up, 6, 9, 15, 17, and that should match whatever pieces of data they gave you on the sheet. What's up, buddy? How does it give you the population if it doesn't know the whole population? There's two separate calculations made for the sample and the population. It gives you both of them because it doesn't discriminate. It leaves it up to you to choose whichever one is best for your particular experiment or results. Okay. So what is the minimum? This is the minimum value of all your data. I'm going to skip over Q1 for a minute. What's the median for those of you that can drive? The middle. The median is the middle of the road. The median is the middle number that divides the data in half, which leads us to Q1 and Q3. They are quartiles. These numbers divide the data into fourths. Do you understand what I mean? A little bit? Is anybody lost? Okay. And max x, that's the maximum value. Where do all these numbers come from that I have in red? These you've seen in 9th grade. This is called a box and whiskers plot. Box and whiskers plot. Okay. Let's also talk about this very famous way of describing data. When you get your SATs back or standardized scores, they give this to you in the little sheet, right? Yeah, it helps determine percentiles. Okay, so let's talk also about this little graph right here. One thing they're going to ask you is, does the data approximate a normal distribution? This graph right here, do you know what a litmus test is? It determines pH. This graph right here is a statistics litmus test. If it's shaped like this, you know what we can do? We can fit a bell curve on it. See it? Can you see that? Okay. If you are able to take, if your graph, if your data, one way to decide whether a bell-shaped curve will fit over it, and thus you can use all those rules that we talked about yesterday, the 68, 95, 99 rule, is if it is symmetric like this, a bell curve probably, most likely fits over it. We have a bunch of criteria that we show you in statistics that you also have to check off. But a bell curve will fit. Let me show you an example of something that won't fit, a bell curve won't fit over. Suppose you did boo. Suppose you did all that work, you got your data back, and your data looked like this. Would a bell curve fit on that? No. In fact, the bell curve would look like this. Do you see that? And that comes up in statistics, and there's different kinds of tests there's a different kind of curve that you have to learn about that helps fit information that looks like this. This is called being skewed. What's up? What's up, Diamond? Oh, no. The line in this box is the middle. That's the middle of the road, buddy. In a bell curve, the middle is the middle of the bell curve. But if it's not a bell curve, the middle can be someplace else. Do you understand what I mean? Kinda, a little bit? All right, guys, let's go. Let's go. Now let's talk about a few things. Take your sheet. We're going to do example number 2. How do you find the range? Does anybody know how to find the range? The range. The range is the maximum minus the minimum. It's the size of this box plot. What is the maximum minus the minimum in this particular case? What's up? Are you sure? Positive. Sure. It's going to be 28. It's going to be 28. But look, you don't actually have to look through the list of numbers. You can just, once you get all of these numbers, right, from doing the calculation, do max minus min. 96 minus 68. Okay, that's the range. That's this total size. And then they ask you about something called the interquartile range. The interquartile range is the size of the box itself. It's where the middle 50% of the data exists. The interquartile range is Q3 minus Q1. 84 minus 76. That's 8. Why is this interesting? The entire data was spread out over 28 units, but the middle 50% of everybody exists within 8 units, which means we could possibly have some people that are called outliers. Do you know what outliers are? What are outliers? They're like way outside. They're still within the box, right? He scored a 40 we talked about, right? What I would say is people like, don't say the person's name, but people that don't submit any of their work. No, we're not going to say his name. People that don't submit any work and don't come, right? Those people are outliers. They should not be counted into the average, the true average of this class, because they really haven't been a part of it. And it will mess up the mean. It will drag it down towards them. When the true average of you guys is much higher without that, him or her. Guys, you guys are about to go ham. What's the next question? What's the next question say? Yeah, does it justify a normal distribution? Does it justify a normal distribution? And here's what I would say to you. Do you remember when we did functions? Remember? Do you remember what I told you to say when they asked, is it a function or not? How do you tell whether something's a function or not? The vertical line test, right? You might have no idea what you're doing, but you know if you see that question, you're going to say it either passes or it doesn't. For statistics, the 68, 95, 99 rule is the equivalent of the vertical line test. If a bunch of data passes that rule, a normal distribution fits. It's like it's a function. And if it doesn't pass this rule, then it's not a function. Then it's not a normal distribution. The problem that you're going to face is that in statistics, nothing is perfect. And so really what we're looking for you to do is for you to mention this and then give your analysis of what you think. Really, yes or no is not a big, we're not even awarding points for that. We're just seeing whether you know about this rule, can remember it, and can apply it. So let me give you all the work needed to do that. Yeah. Let's talk about this for a minute. Before you begin taking it down, let's talk about what's on the board for a second. First of all, the 68, 95, 99% rule says that if you are within one standard deviation, 68% of the data is caught. Within 2 standard deviations, 95% of the data, and within 3, 99% of the data. If that takes place, it turns out to be a bell shape when you try and graph the results. Where did I get these numbers? 1 standard deviation. Where did I get that 79 from? I'll tell you where I got it from. I got it from my calculator. X bar, 79. I just rounded. That's what X bar is. It's the mean. It's the average. I just rounded it. What's up? Where did I get the 7? Where did I get the 7 from? Which one are you using for our scenario? Do we have the entire population or do we have a sample? We have a sample, so we use SX. All I did was take 6.6 and I rounded it to 7, which I know will produce inaccurate results, but we're just talking about ideas today. In statistics, AP statistics or normal statistics, I would literally make you write down that whole number and we would make calculations like that, because that could make or break our analysis. So 79 plus or minus 7 gives me 86 and 72. And what I'm saying to you is find all the numbers between 72 and 86 and count them up. That's what I highlighted in yellow. That's 14. Ooh, because they occur more than once. It's like there were 1, 2, 3, 4, 5 people that scored 84. Do you get what I did now? Yes. So I counted them up, and then I tallied it up, and I said 82%, because 14 divided by 17 is like 0.82. And then I did it for 2 standard deviations, 79 plus twice the standard deviation. That gives me a range of 93 to 65. Turns out 94% of the data, or 16 of these numbers, fall within that range. And finally, 3 standard deviations, I'm catching literally everything. So we had an excellent question say, why is it yes? Why is it yes? The truth is that when they ask these questions, if it's close like this, your yes or no business, your yes or no answer does not matter. That's not what they award the points for. They award the points for you mentioning the 68, 95, 99 rule. And that's it. In other words,
If you said no,
you would have been you would still have gotten it right, because you could have said no, because the one standard deviation away catches 82% of the data, and it was only supposed to catch 68%. And so you could say, I don't really think a normal distribution will fit this data. Even though 2 standard deviations catches 94%, and 3 standard deviations catches 100%. Which one? This one is way off. So you could say no. I would say yes. I would say yes for this particular case, because it did catch 68% of the data. And then 2 standard deviations caught 94. And then 3 caught 100. It's like kind of close. And in statistics, because I've taught it before and I've been through it, I'm telling you right now, nothing is perfect. You will never catch a situation where it's 68 exactly. All right? On your Regents exam, they will make it absolutely blatantly obvious which one it is. Like on your Regents exam, if it mattered yes or no, you would catch something like 20% of the data within 1 standard deviation. Yeah, like this is a question where it doesn't matter either way. All that really matters is that you mention the 68, 95, 99 rule. But if it did matter, it would be, I mean, like blatantly obvious. Even at 3 standard deviations, you would maybe catch like 60% of the data. You'd be like, it's so absurdly off, there's no way. You know what I mean? That's it. Guys, the very last part of our lesson talks about the variance. Talks about the variance. But I'm going to show you the answer real quickly, and then I'm going to give you a scenario. The variance equals the standard deviation squared. And here's the example I want to give you. Okay? Is it possible that 2 students can have the same average, but one to be a better student than the other? Okay? Give me an example of how. Troy. Someone could cheat. Let me give you an example. Student A takes 5 tests and gets 80, 80, 80, 80, 80. What's his average or her average? Student B gets a 64, 100, 72, an 85, and a 76. And I'm telling you that I haven't entered those into a calculator, but I'm just giving you like see how this student was erratic? Yeah. His average turns out is also an 80. But who's the better student? It depends. It depends on what you're considering better, what you're looking for. The variance, though, so if you were to look at those students just based on their average, you'd have no idea who to pick. The variance tells you how spread out their scores are. A really low variance tells you the scores are really close together. A big variance tells you they're further apart. And so the variance equals the standard deviation squared. And all you do is take the sample variance, the sample standard deviation, square it, you get the sample variance. And if you wanted the population variance, you would take the original number from your calculator. Let's see if I could print it up. And square it. So all I did was take this number and square it, and that number and square it. You know, that also depends on your data. It depends on whether you're a person examining bacteria, in which case you're dealing with really, really low numbers, or a scientist, an astronomer examining distance between stars. Okay, you could end up with a really big number. It's in the context of your work. One thing I want you to think about is sample and population. Why would the sample variance inherently be bigger than the population variance? Leslie? Exactly. The sample has less scores. It could just be the case that you got a random collection of people who were biased. And so the scores inside the sample are inherently more spread out than the entire population, right? Where you have this broad spectrum, and this is the more true one, if you could actually get it. The closer this is to that, the closer you are to the truth. The closer the sample variance is to the population variance, if you could even find it, the closer your experiment is to the actual real truth of what it is that you're looking for.